And now let's say the next process, how to exchange the database, right? And here is a full topology. We have two router, route 1 and route 2, and the route ID is 1.1, route ID is 2.2 of route 2, and the connected network is 172.16.1.1 and 1.2. And about route 1, we have two segments 10.10.10.0/24, 192.168.1.0/24. And about the route 2, except these two segments, we still have the new one, 172.16.10.0/24. And if we run the OSPF protocol, we hope route 1 and route 2 in the IP routing table, we can know all the segment information. So next step, if we're running OSPF protocol successfully, they will send out the hello message and to find the OSPF neighbor. Then if we establish the neighbor relationship successfully, then we will to exchange the second packet. We call it DBD packet, database description message. And after we send out this message, the state will be changed from two-way to start. I start exchange information because my route ID is 1.1.1.1 and use a DBD message. And what's the function of DBD message? The first one about OSPF package. Each package we will use a sequence number, because according to the sequence number, then we can provide the acknowledgement. For example, I send you the message 123. If you give me the acknowledgement that I hope to receive the number 4, that means the first 3 packets already sent successfully. So which sequence number will be used? From route 1 definition or from route 2 definition? This is the first DBD message function. I will send out the DBD message and tell you I want to exchange the information because my route ID is 1.1.1.1. And then route 2 also will send out the DBD message. No, I will start exchange information first because my route ID is higher than yours. So compare with 2 route ID. Finally, route 2 route ID is higher, and we will use the sequence number of the route 2. So this is the first message. And then the route 2 will send out the DBD message, right? Because we have to select the summary information and compare which segment I lost and which segment maybe you don't have, but I already have. So this summary information will be added into the DBD message. And after we send this DBD message, the state will become exchanged. Then the route 1 receives this one and will send the summary information to route 2. This is the summary information of my link state database. And in this process, the sequence number depends on route 2. And now the status will become exchanged. And later, after we compare the summary information, we will find that route 1 only have 2 segments. One is 10.10.10 and another one is 192.168.1.0. But compare the summary information from route 2. I don't have the segment of 172.16.10.0/24. So I will send a new message, LSR message. I need your complete information about this segment I don't have. And after we send out the LSR message, the status will be changed to become loading. And route 2 also will send the LSU message. And in this message, we will have the detailed information about this segment. 172.16.10.0. So about the detailed information includes what's the IP address, what's the mask, what's the cost value, something like this. This is the LSU message. And if route 1 already received everything, the status also will be changed from loading to full, and then gives the acknowledgement. I received it, thank you for your information, and use the last type of message, LSACK. LS acknowledgement message to show you that everything I can get it. So this is a process how to exchange the link status information. In the real network, maybe not only one LSA that route A don't have. Maybe we have lots of information. And we can encapsulate lots of LSA in the same LSU and then send to my neighbor, finally to synchronize the database. So this is the full step. And in this process, except the IP address is a mask, the other value is very important, is the cost value. If we synchronize the LSDB, later we will do the calculation to select the best path and add into the IP routing table. And how to define the best path? About OSPF, we will use a cost value to calculate. And the cost value is based on the bandwidth. Higher bandwidth, the cost value will be smaller. So the format is default calculation base and divide the physical link bandwidth in bit. And the default calculation base is 10 to the power of 8 bits. That means 100 Mbps. So if the interface bandwidth is 100 M, the cost value is 1. And the bandwidth is 10 M, the cost value will become 10. So finally, we will select the 100 M bandwidth interface as the best interface. And another one, if there is a decimal result, the decimal part will be rounded off. And for example, if the bandwidth is 1000 Mbps link, the cost value also will become 1. And the cost value of OSPF root entry, we have to use the original cost value of the root and plus the cost value of the inbound interface along the way. If you pass through 3 routers, we have to use 3 routers inbound interface, add all the cost value together. So this is a basic one. So now we will have an example. For example, now we have 4 switches or maybe router connect with each other, and we have different bandwidth link, right? And the yellow one, the bandwidth is 100 Mbps, but the white one is 1000 Mbps. So we hope if the information, the message from the segment 10.1.0 to the destination 10.2.0.0, we can select the white line because the bandwidth is higher. But according to the calculation, because the default bandwidth base is 100 Mbps, so finally all the physical interface, the cost value will become 1. So in the result, according to the calculation, if we choose the yellow one to become the path, the whole cost value will become 2. But if you choose the white one, the cost value will become 4 will become 4. So according to the cost value, we will select the yellow one to become the best path. But according to the bandwidth, this is a suboptimal path. This is not the best one. So we have to let the OSPF know you have to select the highest bandwidth to become the best path. In the option 1, you can change the default calculation base from 100 Mbps to become 1000 Mbps. So the yellow one, the cost value will become 10, right? And the command is enter the router OSPF 10 to directly change the reference bandwidth to become 1000. And the option 2, you can only change one physical interface cost value. For example, to enter the physical interface of the yellow line and change the cost value to become 200. So these two commands also can let the router select the white path to become the best path, but we have different influence. If you direct it to change the default calculation base from 100 to become 1000, all the interface you running the OSPF, the cost value will be changed. But if you only enter the physical interface to change the cost value to become 200, only this interface will have changed the cost value. The rest interface still uses the format and calculates the OSPF value. So this is the command you can use to change the cost value. And then let's see the next step, how to calculate the root calculation, how to calculate the root and add it into the routing table. Now we have one router, route 1, and we have a lot of routers to connect with each other and wait to network A and network B. Each OSPF router will use the SPF algorithm to independently calculate the shortest path to each destination based on its own LSDB. So that's why we have to synchronize the database, right? And then we can get all the network information and select my router to become the first router to calculate the destination. And after the synchronization, the LSDB must be same for the OSPF routers if they in the same area. Pay attention. About the LSDB will be divided into multiple areas, and in the same area, the LSDB should be same. When you, for example, use the route 1 and have the LSDB, and finally, when you use the command show IP routing table, and you can find the result, what's the destination, and what's the administrative distance, and what's the cost value, something like this. And pay attention, if we get the LSDB successfully, and the router will use the SPF algorithm to do the calculation automatically. This step we don't need to add any command. And the optimal route calculated by the SPF algorithm load to routing table, conform to route loading rules. For example, about route 1, if we wait the destination network A or maybe network B, we have special segment. And then if we only have one choice from the OSPF gather routing information, finally this information will be added into the routing table. But if you have the other choice, like the static way or maybe the other dynamic protocol, the administrative value is smaller than the OSPF. Finally, we will select the best one according to the administrative distance value and add it into the routing table. So pay attention about this one. And in the multi-access broadcast network, for example, we use the Ethernet interface. The default OSPF network type is broadcast. That's why we need to select the DR and the BDR to reduce the adjacency relationship, but finally we still can get the correct database information. And the DR and BDR are enabled to establish adjacency with the other router, we call it DR other, and the status will become full. And the DR other only will establish the neighbor relationship with the other DR other routers, and the state will become two-way. And we don't exchange the LSA information. But how to get the LSA information? We will select this information from DR and BDR. And this is the basic about the OSPF concept, how to exchange the hello packets, the DBD message, and also the LSR, LSU, LSACK. Finally, we can get the same LSDB. And there are also the other question is if we have lots of router in our network, why we choose the dynamic routing protocol? Because maybe your network is large and maybe a little complex. So in this scenario, if you use the OSPF and make all the router in the same area, there are some other problems we will have. All the router in the same area need to update the LSA when the link changes to keep the LSDB synchronization. For example, we say about the OSPF function. The first basic function is get the routing information, get the link state information, and synchronize the LSDB. Finally, calculate the routing information. The second one is if the link is broken or maybe we add some link, that means the network topology is changed. We also hope that the dynamic routing protocol can exchange this topology information to my neighbor. You have to update your database and calculate the routing information again, right? So this is a basic one. And if all the router in the same area, that means if one link is broken, we will let all the router to do the calculation again. And any other oscillations in one of the internal links will trigger the network-wide router to recalculate the SPF algorithm. And when you do the recalculation, you need the resources to finish to calculate the correct routing information. So the other one about the intro area, the routes cannot be aggregated because maybe in your network you have lots of segments. You want to do the aggregation to reduce the routing entry in the router. But if all of them are within the same area, we cannot do this function, right? And if your routing table is very big, you will need a longer time to get the best path. And if one link is broken, you still have to change your topology of all the router. So there are some problems. The first one, excessive consumption of resources and the performance degradation. And the second one, I have received too many LSA notifies. Maybe your one link is up, down, and all the router have to receive the new LSA information. And the routing table I need to maintain is very big, and you cannot use the aggregation to reduce the entry number. And maybe because the network topology is changing, you have to use the SPF to do the calculation all the time. So how to avoid this problem? We can make multiple areas to separate large network into smaller, manageable areas. And we can control the LSA to flood only in the region. And we can effectively keeping topology change within the region and limit the impact of topology changes to the region. So this way, like for example, now I am located in the city A, and my neighbor city is city B. If one link is broken, for example, this link cannot be used for the car on the city B. I don't have to change my map of the city A, right? But if the city B is broken, I must change my map. But if the link on the city B is broken, it doesn't matter because now I don't go to the city B. So this is the advantage. And we can improve the network stability and scalability. And we also can do the route aggregation be different areas. On the area boundary, we can do the route aggregation. We can reduce the routing table. So this is an advantage. So maybe you have lots of routers, but you can divide them into different areas. And in the area, we have some special meaning. And in the same area, they were directed to exchange the information with each other. And also, in the other area, all the routers will exchange the LSA information to get the detailed link status information. But pay attention, in this topology, we only show you the LSA exchange in the same area, but at the real network. Also, some areas have to be sent through different areas, because finally the router have to know the whole routing information. But between different areas, the LSA type is different. And according to the LSA in different areas, we can control this LSA, for example, to do some route aggregation. That's why we say if you use the OSPF, not only 5 types of the packets of the message type, but we also have lots different types of the LSA. Some LSA only can be flat, only can be sent out within the area. Some LSA is used to exchange between different areas. So, about this detailed LSA, maybe we will explain in the RCNP course. If we divide multiple areas and different areas, we will have the ID to identify, and we will have the value. We can divide multiple regional hierarchic areas, like the backbone and the non-backbone. We only have 2 types of areas. One is backbone and another one is non-backbone area. And the backbone area means this area ID will become 0. And the backbone area cannot logically be divided. That means all the routers have to within the same area. And you cannot between the area 0 to connect with the other area. Non-backbone area means all the areas, not the area 0, will become the non-backbone area. And the non-backbone area must be connected to the backbone area. So this is the area. And the boundary is a router. That means one router may belong to multiple areas, use different interface. Like this topology use area 0 to become backbone area, and the rest of 4 areas may be area 1, area 2, area 3, and area 10.1.1.1. So this is the reason why we use multiple areas. And of course, this router, this interface belongs to which area depends on your configuration. When you do the configuration on the router, you have to add the command to let the router know this interface belongs to area 1 and the rest interface belongs to area 0. Because we divide multiple areas, then the router will have different type. Like this topology, we have area 1, area 0, and area 2. And different type of router, we can create a different type of LSA. Then we can do some management. And the first one is IR, internal area router. All the interface belong to the same area. And this router we call is IR router, because all the interface belong to the same area. So in the same area, all the IR router will have the same LSDB, like the first router, right? And the second one is ABR, area border router. The interface belongs to 2 or more areas, and one of the active interface belongs to area 0. So this router we call is ABR. ABR will maintain separate LSDB for each region they are connected to. Like the ABR router connect with area 1 and area 0, we will have 2 LSDB. like the map of city A and city B. And the inter-area routing information must be passed through the ABR. How to get the LSA information from area 1? We have to wait the ABR to forward the message to the other routers. So this is ABR. ABR is very, very important. We can do lots of information on the ABR router. And the rest router we call is backbone router, BR. BR means at least one physical interface belongs to the area 0. And this router we can call BR router. At least one interface belongs to area 0. So the media router will become BR, and ABR also will become BR because at least one interface belongs to area 0. And the next is ASBR, Auto System Border Router. A router at the border of an autonomous system has at least one interface belonging to a routing protocol rather than OSPF, and this router we call is ASBR, like this router. For example, maybe this router will connect with other AS uses the RIP protocol, and we will do some router distribution action to add the router into the OSPF, some action like this. And this router we call is ASBR. So these are different router types. And about this router, how does the router know I am the IR or ABR or BR? Depends on your configuration. If you add multiple router on one if you add multiple area on one router, and this router will know I am the ABR. Of course, at least one area belongs to area 0. So this is the different router type. And the next video, we will talk something the basic configuration of OSPF.
Hello guys! Now I think you already know the detail of the OSPF principle, right? And about the OSPF, the main function is help the devices to calculate the routing information. In this scenario, we will maintain 3 tables. The first one is the neighbor table, to record all the neighbor information, what's the router ID, what's the physical interface, something like this. And then we will exchange the routing information, we call it LSA. Then we will add this detailed information in the database. This database we call it LSDB. Finally, we will calculate the routing information, and this information will be added into the OSPF routing table. So these are main 3 tables we have to maintain. And how to make the table get more information? We will exchange the parameters. We will exchange some packets. And about the OSPF, we have 5 types of packets. The first one is hello packets. Say hello to find our neighbor and to record the neighbor information. And the second one, we will use the DD packets and then to exchange the main information between different devices. If we found that I cannot get some information but you have, then we will ask to our neighbor and to give us the detail. And how to ask this question? We will use the LSR message. And the neighbor will update to you use the message of the LSU. When I receive the detailed information, I will give you a reply. I have to check with you. I already received the detail. This message we call is LSACK. So, in this scenario, we can get everything from the neighbor and finally to get the whole network information. Of course, how to solve the problem that if your network is too big, we will exchange so many information if your network topology is changed. We will divide the OSPF to become several areas. And in different areas, we will have different rule of the router. The main router we have to know is the ABR because this device is special. And we will divide this different area, have different area ID, and the special one is area 0. We call it backbone area. So that's all about the OSPF. If you want to know more detail, please follow me together about the next video. We can do lots of practice together. Thank you.